Today we are going to discuss elasticity. What is elasticity? What is the stress and how it is different from pressure? Then we'll discuss what is a strain and what are the different types of a strain. And after that, we'll discuss what is Hooke's law and what are the different modulus of elasticity. So all these we'll discuss in today's discussion. Elasticity is the property due to which a body tries to regain its original configuration after the removal of deforming forces. Like you have a body, you have deformed that body. So after the removal of that deforming forces, if the body tries to regain its original configuration, this is because of the elasticity there. And this change in the configuration may be of different type. It may be a change in its length, it may be a change in its volume, it may be the change in its shape there. So all these will be there produced due to deforming forces. Here we are using the word deforming forces. Deforming forces will be the one which will produce a change in the configuration of a body. So deforming forces we can say as the force, deforming forces of force. It is the force which produces a change in configuration of a body. So that we call it as the deforming force. Like you have a wire and you have stretched that wire. So you are changing its length. So the force which you are applying to produce this change of the length is the deforming force. Similarly, you have a ball and you are compressing the ball. So there also it is the deforming force, that is the force which you are applying to change its volume, that will be the deforming force there. So this will be the one which will produce a change in the configuration of a body. And here we have a term that is called as the stress. So a stress we define, it is the restoring force developed per unit area of a deformed body. You have a body, you have deformed that body. So in that deformed body, there will be a force developed there which will try to regain its original configuration. So the force which is developed per unit area, that will be called as the stress there. Remember, it is different from pressure. Pressure is the force you are applying on a body and the force per unit area will be the pressure there. But this stress is due to the internal force there, which has developed due to a deformation which is produced in the body. So whatever restoring force is developed in the body per unit area, that will be called as the stress. So stress, what we can write? This is restoring force per unit area. Now, if you take what is the dimension of a stress? So a stress, if you consider its dimension, this is your restoring force by area. So in that case, this is your force, which is your mLt minus 2 divided by L square. So it is your mL minus 1 T minus 2. This is the dimension of stress. Similarly, if suppose you want to find what is the unit of a stress, so the unit of a stress will be Newton per meter square. Why is it so? Because this is your restoring force per unit area. So it will be Newton per meter square, or it is your Pascal. If you take the different types of stress, we have normal stress and tangential stress. Let's first take what is normal stress. if the deforming force acts normally over a surface of a body, then the internal force developed per unit area of that deformed body is called normal stress. So here you are deforming a body, and the force which is acting on the body to deform it is acting normal to the surface of the body. So in that case, the stress which is developed is called as the normal stress. Now you can see that we have a body, or suppose we take a rod and we are stretching that rod. So I can stretch it. So here the force which I am applying on the body, it is acting normal to this particular surface, so that there is an increase in its length. So if this happens, the restoring force which will be developed, that is your normal stress. Again, you may have a body on which we are applying force. Again, it is normal to this, but we are trying to compress it. This time we are trying to compress this one. So this is also normal stress. Normal stress we can classify in again 3 categories. Here first one is called as the tensile stress, second one is compressive stress, and third is your hydraulic stress. Like we have taken, suppose a rod, and we are stretching this one. We have applied force and we are stretching it. So in that case, if there is an increase in its length will increase. So if in the body there is an increase in the length due to the applied force in its direction, then the stress developed in the body is called as the tensile stress. You have the body, you are stretching it, and you are increasing its length by stretching it. So here the stress which is developed, that is called as the tensile stress. Remember, this is the normal stress because you are applying force normal to the surface, so that there is an increase in its length. So this is a type of normal stress and we call it as the tensile stress. In the same way, if there is a decrease in the length, you are applying force on this body and you are trying to decrease its length because you are exerting force there normal to the surface, and there is a decrease in its length in the direction of the applied force, then in that case the stress developed, that is called as the compressive stress. So this is also another type of normal stress. Third type of stress is there, that is called as the hydraulic stress. Hydraulic stress will be there if you are deforming a body and there is no change in the shape of the body, but its size is changing. So that stress which is developed in the body, that is called as the hydraulic stress. Like suppose you take a spherical body and you put it in a fluid under high pressure. So what will happen? That fluid will try to compress this ball from all directions. So the force which will be acting on the body, or the deforming force, will always act normal at every point on that body and will try to decrease its volume. So its volume will decrease, but not its shape. Shape will remain spherical there. So in that case, whatever force is developed in this body, that is called as the hydraulic stress. So this is also again another type of your normal stress, because here also the deforming force was acting normal to the surface of the body, because the force was acting at every point in the perpendicular direction there to that particular cross-sectional surface, if you consider. So that is the hydraulic stress. Then we have another type of stress, that is called as the tangential stress. Now, tangential stress will be there, like you have a body. Suppose if you take a body and this surface, suppose we just try to keep it fixed and we exert force on this surface, that means we are exerting a force tangential to the surface of this body. So in that case, what will happen? The body will get deformed like this. So here, this force, if it is F and this is your A, so the tangential force which is acting on the body and it is deforming it, then the stress which is developed in this particular body, that is called as the tangential stress. So tangential stress is if the deforming force is acting normally to the surface of the body, changing its shape is getting changed, but not its volume. So the restoring force developed per unit area is called as the tangential stress, and this is also called as the tangential stress, or you can call it as the shearing stress. So again, if you calculate this one, how much it will be? This will be tangential stress. This will be the tangential force divided by the surface area. So it is your F by A. So this is also another form, but of course dimensionally it is the same stress we are taking. So this is the tangential stress. Next is the strain. If you have a body, you have deformed it. So if you are deforming it, there is a change in its configuration. So a strain will basically give you a measure of that change. In fact, this is the change in configuration per unit original configuration of the body. So a strain is, it is the change in configuration per unit original configuration. So that is your strain. Now, as the configurational change may be of different types, it may be a change in the length, it may be the change in the volume, it may be the change in the orientation of the body. So accordingly, this strain is also of different types. Like the first one is longitudinal strain. So this is the longitudinal strain. It is basically change in length per unit original length. You have a body, you have deformed that one. Like you have a wire, you have stretched it, or you have compressed that one. So the change in its length per unit original length, that will be called as the longitudinal strain. So it is the change in length per unit original length of a deformed body. So that is your longitudinal strain. Like suppose I have a body, or suppose you have a rod there, you have stretched that one so that its length has changed. Suppose originally this particular one was having a length L, and now due to the applied force on this body, the new length is now L plus delta L. It means what is the change in the length? That is your delta L. So this longitudinal strain here, this will be equals to change in length delta L. What was the original length here? L. So this is delta L by L. So this is your longitudinal strain. Volumetric strain. This is change in volume per unit original volume of the body. So it is a change in volume per unit original volume. You have a body, you have deformed that one, there is a change in its volume. So here this volumetric strain, if you consider, it is the change in volume divided by original volume. So this will be your, suppose delta V we use to represent the change in the volume, and this divided by V, which we assume that it is the original volume. So this delta V by V will give you the volumetric strain. Now for the shearing strain, this is the third type. Shearing strain. This will be there when you have a tangential stress developed in a body, or you have, suppose, a tangential force is being applied on a body, there is a change in its shape. Like suppose you have this body and this is suppose fixed. We are applying force on this surface. This is your F. The body gets deformed like this. So this is theta. That is the angle through which this surface gets turned. So this will be the measure of this particular angle through which it gets turned. So shearing strain is the angle through which the plane perpendicular to the fixed surface gets turned due to the tangential force applied. Like here we had this particular body on which we have applied this tangential force F. The body is getting changed its shape like this. So here this particular surface is the normal surface. That means this is the surface perpendicular to this fixed surface. So this surface gets turned here by the angle theta. So this theta will give you the shearing strain here. So this will be theta. Now you can also measure this in terms of what distance it has turned this surface. Suppose this is your delta x, and this is at a distance, suppose L. That means the tangential force is applied at a distance L from the fixed surface, and delta x is the distance through which the surface gets turned or it is moving there. So in that case, this theta can also be taken as your delta x by L. And what is this particular theta? This is basically your shearing strain. So this is your shearing strain. Either you can measure it in terms of the angle or in terms of the ratio of the distance through which this surface gets turned when we have applied a tangential force there at a distance L from the fixed surface. In fact, for the measurement of theta, you will be using this particular expression also there. You can use this delta x by L to calculate theta. So that is the measure of the shearing strain. Remember, all strain which are basically the change in configuration to the original configuration ratio. So it is basically a dimensionless quantity. So it is a dimensionless quantity because it is the ratio of same physical quantity. And also it will not have any unit because it is dimensionless, and definitely in this case we can say that it does not have any unit there. Let's now take Hooke's law. Hooke's law says that within proportionality limit, a stress is directly proportional to a strain. So this is that within proportionality limit, a stress is directly proportional to a strain. So what we are saying, that within proportionality limit, a stress is directly proportional to a strain. So you have a stress, this is proportional to a strain. Now if you remove this proportionality sign, you will get a constant of proportionality. So this can be written as stress equals to the constant of proportionality. That constant of proportionality is called modulus of elasticity. into strain. So stress is equals to modulus of elasticity into strain. The constant of proportionality, we are calling it as the modulus of elasticity. Now this modulus of elasticity has been given different names depending upon for what type of changes we are using them. So this will be of different name there, like it is the Young's modulus of elasticity or bulk modulus of elasticity or modulus of rigidity there. So we'll see that how we get those terms there and in which cases they are applied. One more thing you remember, we are saying within proportionality limit. We are not saying within elastic limit. In many books you'll find that it is written as within elastic limit. But when you will do a stress and a strain curve there, you'll find that proportionality limit and elastic limits are two different points. And this Hooke's law is obeyed only in the range up to the proportionality limit, not up to the elastic limit. Of course, in some books you may find safely they have written that within small deformation or for small changes there. So within small changes, stress is directly proportional to strain. That means you are applying small changes there. That means you are not reaching up to the proportionality limit. Definitely in that case, this will be applicable there. Or you can directly show that stress is directly proportional to strain. So we'll do in detail how that one is a proportionality limit different from elastic limit and why we are not saying that it is up to elastic limit and it is within proportionality limit only. We are considering this Hooke's law. Now let's take different cases there. Like suppose if I take Young's modulus of elasticity. Young's modulus of elasticity. Now this is, suppose we represent it as your capital Y. This is basically capital gamma. So Young's modulus of elasticity is that within proportionality limit, it is the ratio of longitudinal stress to longitudinal strain. So within proportionality limit, it is the ratio of longitudinal stress to longitudinal strain. So that means what we are saying that Young's modulus of elasticity will be equals to longitudinal stress by longitudinal strain. How we get that one? The expression for this. Suppose we have a rod or we have a wire. Its length is suppose capital L. And we are applying a force F which produces a change in its length by delta L or a small l. Suppose the area of cross section of this one is A. We have a rod of area of cross section capital A, length capital L, on which we have applied a force F there, which produces an extension small l. So what will be the longitudinal stress here? Longitudinal stress will be F by A, force developed per unit area of cross section, divided by strain. What is the strain here? It is the longitudinal strain. So it is the change in length per unit original length. So this is your small l by capital L. So this term, if you consider, it is your FL by AL. This is the expression for Young's modulus of elasticity. F is the force there, capital L is the original length, A is the area of cross section, and the small l is the change in length there. There is a very interesting question which is often asked there. Which one is more elastic, steel or rubber? In day-to-day life, the way we are using the elastic bodies there or elasticity, here it appears that rubber is more elastic because we have noticed more change there in rubber there, and when you remove the deforming force, it easily regains its original shape. But in language of physics, if you consider here Young's modulus of elasticity, we have taken as FL by AL. The material which will have more value of Young's modulus, that will be more elastic, or the material which has more value of modulus of elasticity will be taken as the more elastic. So suppose we take two wires or two rods, one made of steel and other made of rubber. Both have same length. That means we are taking the length of the steel wire same as length of the rubber. Similarly, we take a same area of cross section also. So A is also same for steel and as well as for rubber. And we want to make the same change in the length. That means change in length in steel should be same as change in the length in rubber. So what basically we have done, we have made this L, A and a small l all same. So it is suppose constant here. And if it is such, then what we'll get, modulus will be proportional to F, that is the applied force. If you consider LA and small l to be same or it is constant there, then Young's modulus will be directly proportional to the applied force. Now you just take in the day-to-day life case, you have the steel wire, rubber wire there, same length, same area of cross section. You want to produce same change in the length. So where you will require more force to be applied? Definitely in case of steel. So obviously, as you will require more force, so Young's modulus will be more. So steel will be more elastic than rubber. Another type of modulus of elasticity is bulk modulus of elasticity. This is normally represented by capital B. So within proportionality limit, this will be the ratio of normal stress to volumetric strain. So in this case, within proportionality limit, it is the ratio of normal stress to volumetric strain. So that means we can write this one as normal stress to volumetric strain. So if I take suppose a small p to represent the normal stress or the change in pressure applied on the body there or developed in the body, and volumetric strain is suppose delta V by V, change in volume by original volume, then B will be given as P by delta V by V. Here you can notice there will be a negative sign there. This negative sign is simply indicating that an increase in pressure will cause a decrease in the volume or vice versa. So here, if you're changing a pressure there, that is the normal stress, increasing it, there will be decrease in the volume of the body. So that is why this negative sign is there. Another term is there, that is the compressibility, we represented by capital K there. This is basically reciprocal of bulk modulus of elasticity. So it is the reciprocal of bulk modulus of elasticity. That means we can take K as 1 by B. In many numericals and other, you will find whenever suppose you have to find the change in volume there or volumetric strain, then definitely you require the term there which will be the bulk modulus there. Data should be given there. but they will not give the data of the bulk modulus. Instead, they will give you the data for compressibility. And if you know that compressibility is the reciprocal of the bulk modulus, you can easily get that value of the bulk modulus. You can substitute it in the formula and get the required quantity there, whatever is asked in that particular numerical. Next term is the modulus of rigidity. This is within proportionality limit. It is the ratio of tangential stress to shearing strain. So this is modulus of rigidity. This is equals to tangential stress by shearing strain. Like you have here a body. Suppose this surface is fixed. We are applying force F. Surface area is A there. And this one gets turned there by theta. So tangential stress, we can write F by A. Tangential force by area. So it is your tangential stress, and shearing strain there will be equal to theta there. So with that you can calculate what is the modulus of rigidity. Or in terms of this delta x and L also you can get this one. So this is your say F by A divided by delta x by L. This will give you the modulus of rigidity there. These were the terms which have been used there in elasticity chapter there. Different expressions there for strain, different types of stress, and also the different modulus of elasticity and how we express them.